In the last video, I mentioned that we'll be learning about 5 different types of electrophilic aromatic substitution reactions. In this video, we'll review that first one, so halogenation. In halogenation reactions, we are adding a halogen to an aromatic ring. So we can do this with bromine and with chlorine. For the general scheme and for the mechanism, we will do that with bromine, but it's analogous if you're adding chlorine. So we have our benzene ring. We add Br2. Now, Br2 is a stable molecule. It's not reactive enough to react directly with benzene. And so that's why we need a metal catalyst to make bromine a better electrophile. Scientists use iron or iron tribromide. With those catalysts present, or with one of the catalysts present, we end with bromobenzene. And then a byproduct is HBr. So let's first talk about this catalyst, iron or iron tribromide. You can have either present in the reaction mixture, because if you only have, let's say you only have iron, and we add, of course, Br2 to the reaction, if these two are in the presence of each other, they generate iron tribromide. So you can have either listed. And you'll certainly see both in example problems. Okay, so what does iron or iron tribromide do in this reaction? Why do we need to include it? Well, let's say we have our Br2, so two bromines bonded to each other. Again, as I mentioned, this is a pretty stable molecule. Bromine in this molecule, and Br2 is not a very good electrophile. But if we add the iron tribromide, this iron acts as a Lewis acid. Remember what Lewis acid means. That's when we have an atom that has an open valence shell, so it can accept more electrons, can accept additional electrons. A common example, I'll write this off to the side, of a Lewis acid is boron trifluoride, because boron is stable with an open shell, but it can accept more electrons, so you can add additional electrons to this boron here. Same thing is true for iron in FeBr3. So because it is a Lewis acid, it accepts electrons from one of the bromine atoms. So now this is a curved mechanism arrow that I drew at the bottom there. And that generates a new product where we have the first bromine bonded to now the second bromine, which is then bonded to iron tribromide. That gives iron a negative charge and this bromine a positive charge. So that bromine in the center with a positive charge that is very electron deficient. It pulls electron density away from the bromine at the end, the neutral bromine. And so that makes these bromine atoms much more reactive than if you just have the Br2 molecule present. So the positively charged bromine is pulling electron density away from the bromine at the end. The electrons shared in the bond are going to be closer to that positively charged bromine because it is lacking electrons. And so that makes this bromine now electrophilic. This is going to be our electrophile. This bromine here is now a better electron acceptor. Here we go. So when this large bromine molecule reacts with a benzene ring, you'll see that the positively charged bromine accepts electrons, and that's favorable since it's positively charged. All right, so now let's do the full mechanism, starting with benzene, using this catalyst and ending up with bromobenzene. All right, starting with benzene. And I'm only highlighting that one hydrogen because that's the one that will show being removed. You can do it for any hydrogen around this ring. We have that bromine complex with iron. Now remember, this bromine here is the electrophile. And this entire part of the molecule we can call a leaving group, or LG for short. It's a leaving group. It will leave after the bromine is substituted. So the bromine at the end is electrophilic, the one that I've labeled as the electrophile. If we look at benzene, now we think about where are there electrons that can be donated to or shared with the electrophile. And those are electrons in the pi bonds. So I will select the pi bond adjacent to the carbon where we've drawn out that hydrogen. Again, you could choose any pi bond, just one of them. Those electrons will form a bond with that bromine, which is our electrophile. And then the electrons in the bond between the neutral and positively charged bromine will be owned by that positively charged bromine. So that catalyst helps this reaction move forward by making this more reactive bromine molecule. So the result of this step is that we now have a broken pi bond in the benzene ring. So the two that I did not draw the arrow from are still present. But there is now a new bromine bonded, and I'm showing that bonded to where that highlighted hydrogen is. That results in a carbocation. So we open the shell of that carbon. So in this step, we form a secondary carbocation, which we know is a relatively unstable carbocation, but in this case, this carbocation is stabilized by resonance. So let's draw the resonance structures, and we'll draw that underneath here. So this is not, actually I'll just do this in purple to help distinguish that this is not part of the mechanism, but it is showing the resonance that's possible for this intermediate. And essentially what we can do is shift around the pi bonds. So let me redraw it over here. We'll use our resonance brackets. We could move that pi bond to create a pi bond where the carbocation is, and that shifts our carbocation to be at this carbon. And then we could move that pi bond, and we have a carbocation at a different carbon. So although a secondary carbocation is relatively unstable, when we have this bonding pattern, the carbocation is stabilized by resonance. Now, one important thing to consider here is whether we have an aromatic ring at this point. You might see that at this carbon that I'm highlighting in blue where we added the bromine, that's now an sp3 carbon. So this intermediate is not aromatic. We no longer have a cyclic arrangement of p orbitals, of unhybridized p orbitals. In breaking aromaticity, so going from something that's aromatic to something that's not aromatic, requires a lot of energy. This is another reason why we require that metal catalyst to carry out this reaction. Okay, so we have our carbocation, non-aromatic intermediate that's stabilized by resonance. Now the byproduct of that first step, so the bromine that leaving group from that first step is now reacted with this molecule to remove the hydrogen that's at the sp3 carbon. So the electrons in the bond between bromine and iron will remove this hydrogen. Then the electrons in the hydrogen to carbon bond reform a pi bond between the two carbons, and this reestablishes aromaticity. So now our product here has the 3 pi bonds again. We have the added bromine. We have a bromine hydrogen molecule, hydrogen bromide. And we have FeBr3, which is the catalyst that is regenerated at the end of the reaction. So all 3 of these are products. So if we think about overall reaction, we can say step 1 up here, we generate the electrophile. That is at larger bromine iron molecule, the iron with 5 bromines. Then step 2 here, we form a resonance stabilized, I'll write this step down here, form resonance stabilized carbocation intermediate. Which is not aromatic. And then step 3, we lose a beta hydrogen to form a substituted aromatic product. These are really the 3 steps in this mechanism here. That's everything for the halogenation reaction. Again, you could do the same thing, just replacing all of the bromines with chlorine, and you would end up with chlorobenzene as your product.